Energy is the lifeblood of our modern civilization. From the moment we wake up to the lights of our cities at night, energy powers our world. Yet, as we face the twin challenges of climate change and dwindling fossil fuel reserves, the quest for sustainable, abundant, and clean energy has never been more critical. Among the potential solutions, thermonuclear energy stands out as a promising frontier. This video explores the science behind thermonuclear energy, its potential to transform our energy landscape, and the challenges and advancements that lie ahead. At its core, thermonuclear energy is derived from nuclear fusion, the process that powers our sun and other stars. Fusion occurs when light atomic nuclei, such as hydrogen isotopes, collide and fuse to form a heavier nucleus, releasing a tremendous amount of energy in the process. The most promising fusion reactions for energy production involve isotopes of hydrogen, deuterium and tritium. When these nuclei collide at extremely high temperatures, millions of degrees Celsius, they overcome their electrostatic repulsion and fuse together, producing helium, a neutron, and a large amount of energy. Fusion energy offers several key advantages over traditional energy sources. It produces no greenhouse gas emissions during operation, generates minimal long-lived radioactive waste, and has a virtually limitless fuel supply. Deuterium can be extracted from seawater, and tritium can be bred from lithium, making fusion a potentially sustainable energy source for millennia. One of the primary approaches to achieving fusion is magnetic confinement, which uses powerful magnetic fields to contain and control the hot plasma needed for fusion reactions. The most well-known magnetic confinement devices are tokamaks and stellarators. Tokamaks, like the ITER project in France, are toroidal devices that create a magnetic field to confine the plasma. Stellarators, such as the Wendelstein 7X in Germany, use twisted magnetic fields to achieve stable plasma confinement. Another approach is inertial confinement fusion, which involves compressing a small fuel pellet to extremely high densities and temperatures using powerful lasers or other means. The National Ignition Facility, NIF, is a leading inertial confinement fusion research center, using 192 high-powered lasers to compress and heat the fuel pellet, aiming to achieve fusion ignition. Recent years have seen several important milestones in fusion research. In 2021, the NIF achieved a significant breakthrough by producing more energy from a fusion reaction than ever before, albeit still below the break-even point. Meanwhile, the construction of ITER, the largest and most ambitious fusion experiment to date, continues to make progress, with first plasma expected in the coming years. While the progress is encouraging, significant challenges remain before thermonuclear energy can become a practical and reliable power source. These challenges span across scientific, engineering, and economic domains. One of the foremost challenges is achieving break-even, where the energy produced by the fusion reactions equals the energy input required to sustain them. Beyond break-even, we need to achieve a net energy gain, where the energy output significantly exceeds the input, making fusion a viable power source. The extreme conditions inside a fusion reactor pose severe challenges for materials and engineering. The reactor walls must withstand intense heat, radiation, and neutron flux without degrading. Developing materials that can endure these harsh conditions and maintain their integrity over long periods is a critical area of research. Tritium, one of the primary fuels for fusion, is radioactive and scarce. To sustain a fusion reactor, we need to develop efficient methods for breeding tritium from lithium within the reactor itself. This involves capturing the neutrons produced during fusion and using them to convert lithium into tritium, a process that requires precise engineering and control. Thermonuclear energy, with its potential to provide abundant, clean, and sustainable power, represents one of the most exciting frontiers in science and technology. While significant challenges remain, the progress made in recent years is encouraging and points to a future where fusion could play a central role in our global energy system. Through continued innovation, collaboration, and support, we can unlock the immense power of the stars.